Welcome to International Biorenewables Law and Policy. This presentation focuses on the production of biorenewable chemicals. The reason we need biorenewable chemicals is because when you look at all the products made from a barrel of crude oil, not only do we produce energy products such as liquid fuels, but there's a large category here, simply noted as other products, that have a disproportionate amount of revenue generated. In some cases, it's these other products that actually determine the profitability of a refinery. These products include high-value chemicals, cosmetics, and other type of specialty chemicals that command a very high price. So in order for a biorefinery to become commercially viable, one potential strategy might be to think like an oil refinery where from the same crude barrel of oil, you produce a diversity of products, some of which you might change the amount produced depending on market prices. One concept of a biorefinery is one that's being developed here at Iowa State. And so the idea is that we could take biomass and use pyrolysis technology to convert it into a wide range of products, which includes pharmaceuticals, polymers, fuels, bioasphalt, cement, soil amendment. And so the generation of all these products, each of them can generate a certain amount of revenue. But by generating a portfolio of products, we may be able to not only increase our revenues, but maybe reduce the risk of the biorefinery by producing the most highly valuable product at different market times. And so we're going to explore some of these dynamics in the next couple slides. If you look at commodity fuels and chemicals, particularly those derived from petroleum, what you'll find is that most of these commodity fuels and chemicals are subject to a wide range of prices. So in the case of gasoline, for example, we've seen prices vary from $1.50 to almost $4 per gallon. Diesel has also had a similar change. If you move up to asphalt, cement, and specialty chemicals like benzene, you do see different ranges of variation between these. And what we found is that historically, they're not varying at the same time. And so sometimes you might have high gasoline prices, but low cement prices, or vice versa. And so a biorefinery that can produce these different products could play into those dynamics and generate or maximize the production of a given product depending on their expectation for the market price. We looked specifically at gasoline and diesel, BTX, which are some specialty hydrocarbons, and asphalt as our construction material. Similar to what I showed earlier, the biorefinery, based on the pyrolysis concept, can generate many of these products. If we take the crude oil that's generated from pyrolysis or bio-oil, we can phase separate it into heavy ends and light ends. The heavy ends can generate sugars that can go into the food market, which is a fairly high value market, or they could be fermented to ethanol. The oligomers could be sold as fuel oil or bioasphalt, or even upgraded to gasoline and diesel. Finally, we can also produce gel fuel for clean cooking fuel markets, and about cement for construction markets as well. When you look again at the various combination of products, we have grouped them into fuel products, alternative products or biochemicals, and then hydrocarbon chemicals. And we're showing here the range of values on a dollar per metric ton basis that we've used in our study. The idea here is that in the study, we were going to look at how did these different biorefineries fared under conditions where, for example, fuel was at low price versus chemicals at a high price. Which combination of these products would a biorefinery produce? And does it make sense to have a biorefinery that can produce all these different products? If you look at a biorefinery that only produces fuel, you can see that based on the market value of petroleum fuels, gasoline and diesel being relatively inexpensive, most biorefineries will lose money trying to produce or compete in the biofuel market. However, in the biochemical markets, this is the construction market where we produce asphalt and sugars, there appears to be an opportunity to make some profit. In the hydrocarbon market, this is the benzene, toluene, xylene, or BTX market, there's a modest profit. However, all of this has some uncertainty, and so you can see that from the graphs that for all of these different alternatives, except for the hydrocarbon scenario at the bottom, there is a significant probability of losing money over time. To combat that probability, one strategy would be to have an integrated biorefinery. This is a biorefinery that utilizes 3 different upgrading technologies, in the case of pyrolysis, for example, to produce gasoline and diesel when that's the target product, or sugars and calcium acetate for asphalt, or finally aromatics, olefins, and fuel oil for the hydrocarbon chemical market. This facility, if you have enough foresight, you could decide to build different capacities in terms of how much gasoline and diesel you can produce at a time, or you could have equal distribution of upgrading capacity for the different markets. In our models, we looked at all the different combinations. Maybe you only want to produce biofuels with a small amount of hydrocarbon chemicals, or you want to have equal amounts of all the products. And so when you have the possibility of looking at this portfolio of products, for 3 products, you can envision this as a triangular contour plot. What this contour plot shows is at each corner, you have the production of 100% of that product. So for example, at the very top, you have a facility that only produces fuels. At the bottom left corner, you only produce chemicals, or the benzene, toluene, xylene. And at the bottom right corner, you have your alternative chemicals or biochemicals. This includes your asphalt and sugars. And based on historical prices, we calculated how much revenue the facilities would generate if they concentrate on any of those products, a combination of products. So for example, if you're at the center of these triangular plots, you're producing equal amounts of all the products. If you're at the corner, for example, on the left triangular plot, if you're at the bottom left corner of that plot, you produce the maximum net present value. That's where you make most of your profit, by producing chemicals. And that occurred at one particular time period. However, we found other time periods when fuels had a very high value and chemicals had a low value, as shown on the right plot. And in that scenario, it makes more sense to only produce fuels as your primary product. An integrated biorefinery could, in principle, shut down different parts of their plant and maximize the production of fuels when fuels have a high value. By doing that, or by having that integrated biorefinery, what we found is that the combination of all of these helps improve your internal rate of return. And so if you compare the internal rate of return again of just producing biofuels, we believe it's slightly negative. But if you compare it to producing hydrocarbon chemicals and bio-based products, you can actually get a fairly decent rate of return, even though the facility is integrated. So to conclude, in order to replace the barrel of oil, biorefineries will need to produce a diversity of products. However, these products have a significant market price uncertainty, and so sometimes it's important to consider a portfolio where a facility not only focuses on one product, but a variety of these. We believe that integrated biorefinery is the way to do this because it helps reduce the financial risk of focusing on a single product that might lose value over time. And based on these concepts, the production of biochemicals, I believe, can be a robust strategy for biorefineries if they can take into account the uncertainty in these markets.